Okay. Today's speaker is Professor Nicolás Bernal, and he will talk about ultraviolet frozen in dark matter. So please start.
So first, thank you very much for this super kind invitation. As always, I'm very happy to be at KIAS, even if it's just virtually. I hope next time will be in person. You can hear me, right?
Yes.
Okay. Yeah. So we'll talk. So Dong asked me a very difficult task. Actually, is to talk about these two papers, and so they're not exactly about the same subject, but so I will talk first about one, then about the second one. So the first one actually I did in collaboration with Basabendu Barman. So he's Basabendu. He's a postdoc here actually at Universidad de Narino. And the paper is about strongly interactive massive particles produced gravitationally. And the second is done in collaboration with Yong Shu. He's a PhD student in Bonn, in Germany, under the supervision of Manuel Deves. And I'm telling you all that because he told me that he's very interested in applying at KIAS. So maybe you will hear some news about him in the near future. So I'm Nicolás Bernal from Universidad de Narino in Bogotá, Colombia. Okay. So first, I just want to show you that I'm here, far away, and here is still Monday. So, yeah, that's all. Okay, so let's start in the business. So I think you guys are very familiar with dark matter and with the evidences that dark matter. So as you know, there's this number of observations that indicate the existence of this non-luminous dark matter. Actually, it's like a missing force, missing gravitational force. And the key points that appear at very different scales. For instance, at the scales of galaxies, so at the scale of kiloparsec, we can see this flat behavior of the rotation curve, right? But also that happens at the scales, on much higher scales, for instance, the scale of megaparsecs or so, at the scale of clusters of galaxies, you can see the same flat behavior on the rotation curve. But there's also this very famous bullet cluster that could be explained or that indicates that there's this dark matter, but that also appears at much higher scales, so at cosmological scales with the CMB anisotropies that could be explained and could be very well understood in the framework of the lambda CDM model, where the dark matter, in particular the cold dark matter, plays a crucial role. Okay, so that's the map from Planck, from the CMB inhomogeneities. And there's a lot of information that could be extracted. In particular, we can know what's the distribution of the total matter and energy density in the universe. So I'm from Colombia, so at some point I have to show an arepa. So if this arepa corresponds to the 100% of the energy density, from CMB we know that only 5% or so correspond to baryonic matter. So if you want to standard model, whereas 25% or so correspond to dark matter, and 70% to dark energy. So to this accelerated expansion of the universe that we can see and can measure at present. One thing that I forgot to mention is that we can do this, this talk very informal. So please interrupt me at any point. Please don't wait until the very end for asking questions or making any comment that you have. So please don't hesitate and interrupt me at any point. Okay, so I don't think I have to spend much time trying to convince you about the existence of dark matter and the importance of dark matter. So we know that dark matter is there, but we don't know, however, what it is. However, we know some properties that it has to have. For instance, it has to be neutral, meaning it cannot have a electric or color charge. It has to be massive in the sense that it has to be non-relativistic at the moment of structure formation. It has to have weak interaction with the standard model, but we cannot have in mind electroweak interaction, but interaction that's not very sizable. We don't want it to interact much with the standard model. We want to be dark after all. And it has to be stable or at least long-lived, with a lifetime longer than the age of the universe. And that's very cool because that points towards new physics. So dark matter needs new physics beyond the standard model, new degrees of freedom. So that's why, at least for us, particle physics, this is so exciting. Okay. So one question is, how was dark matter produced in the early universe? So the answer is, we don't know. However, there have a lot of models of proposals for producing dark matter in the early universe. And the most famous and by far correspond to WIMP. So weakly interactive massive particles. So, and I think you guys are also very familiar. So in the WIMP paradigm, it's very simple. The idea is that we have sizable interactions between dark matter and the standard model. For instance, here in this diagram, so the dark particles here, dark balls correspond to dark matter particles that have sizable interactions that can annihilate into these white particles that correspond to standard model particles. So we can have the annihilation, 2 dark matter particles into 2 standard model particles. And the inverse reaction can also happen. So we have the production, so annihilation of standard model into dark matter. And the key point is that these 2 reactions can happen, and actually they happen at the same rate, meaning that we can have chemical equilibrium between the 2 sectors. So that's the key point. So the 2 reactions happen at the same rate, so that both chemical and kinetic equilibrium can happen between the 2 sectors. So here, for instance, I'm showing you a plot of the dark matter yield. So Y corresponds to the dark matter number density normalized via with the entropy density as a function of X, which is basically time. So it's the inverse of temperature, if you want. So the dashed line corresponds to the equilibrium density. So dark matter in the early universe is tracking the equilibrium, and at some point this equilibrium is broken, and you say that the dark matter abundance freezes out, and that's why you generate the dark matter abundance that is observed nowadays. And higher cross-section, higher interaction rate imply the dark matter keeps in equilibrium for longer, and therefore the rate abundance is smaller. So if you want to keep track of the dark matter abundance, you have to solve this kind of Boltzmann equation, where n is just the dark matter number density. So dark matter gets diluted because the expansion rate, where h is the Hubble expansion rate of the universe, and this sigma b corresponds to the thermally average annihilation cross-section, right? So as I told you, WIMPs mean that dark matter is in chemical equilibrium. And for having that, you need cross-sections of the order of the electroweak scale. So meaning at the picobarn scale, and that corresponds to, say, 10 times to minus 26 cubic centimeter per second. So that's a typical interaction rate that one have to have. And also we can have that for dark matter masses in the GV to TeV ballpark. And dark matter freezes out, so you break the chemical equilibrium when the temperature of the thermal bath is around the dark matter mass over 20 or something like this. One interesting point is that this paradigm is completely independent from initial conditions. And it's independent because you reach equilibrium. And equilibrium is like an attractor. So once you reach the attractor, once you reach the equilibrium, you lose all the information about initial conditions. Initial conditions, I mean, for instance, what was the inflationary dynamics. So we don't care here at what temperature inflation happens, how the reheating took place. So it's completely independent of that. So that, as I told you, that is by far the most appreciated paradigm for production of dark matter. However, the problem is that what I'm writing here, over the last decade, a huge worldwide effort to detect WIMP dark matter using a multi-channel and multi-messenger approach has been taken, but there's no complete detection so far. So even if WIMPs are super cool, they have been not been detected. So we need to look for new alternative of production of this dark matter in the early universe. So one possibility is what we call the FIMP, and corresponding to feebly interacting massive particles. And this is very simple. Okay, and it comes in two versions. Sorry. The first one corresponds to the infrared freezing, and you will see why. So the idea of the infrared FIMP is that we will not reach chemical equilibrium. So the chemical equilibrium with the two sectors is never reached. And how can we ensure that? The idea is that the interaction rates are not strong enough. So that even we could have the dark matter production, like this process can happen in the early universe. We will never, okay, or this interaction, the annihilation, will basically not happen. So even if these interactions both could happen, I mean, they will never reach equilibrium. So they will not happen at the very same rate, right? So as I was telling you, the key point is that the equilibrium, chemical equilibrium is never reached. And here we're assuming that the interaction between these two sectors happens between via renormalizable operators. So that's the key point. And that means that the bulk of the dark matter production will happen at small temperatures. So where the temperature of the thermal bath is of the order of the mass of the mediator or of the dark matter mass, right? So that's the freezing temperature. So as I'm showing here, contrary to the WIMP dark matter, here the dark matter is being produced slowly, and the bulk happens where the temperatures are kind of electroweak scale typically, and then you don't have production anymore. You say that the Drake abundance freezes in, and as you can see, it never tracks the equilibrium density. So in order to have that, you need small couplings. And when I say small, I mean a really small couplings of the order 10 to the minus 10-ish, 10 to the minus 11. So these are the typical couplings that you need between the two sectors. One important point is that there's a mild dependence from initial conditions, in the sense that for infrared FIMP, you typically assume that there was no sizable dark matter production in the very early universe. So for instance, at reheating, for instance, you typically assume that the inflator is not coupled to dark matter, so there's no direct production of dark matter via the decay of the inflator. So, but there's a dependence from initial condition, even so I would say that it's kind of mild. Another comment is that these kind of couplings, I mean, people can complain saying that this is unnaturally small because you would naively expect order 1 couplings. However, in some models, this could be technically natural. Yes, so I think that's important to say. So they're very small, but at least they could be technically natural in some models. Okay, this corresponds to the infrared freezing. And if there's an infrared freezing, surprise, surprise, is because there's an ultraviolet freezing. So the idea is very similar. The basic idea of freezing is that chemical equilibrium is never reached. So here is exactly the same. Chemical equilibrium is never reached between the two sectors. However, the main difference is that now we'll assume that the interaction between these two sectors, the visible, the standard model, and the dark sector, or dark matter, the connection is via non-renormalizable operator, right? And from the phenomenology point of view, there's a big difference is that now the bulk of the dark matter is not produced at low temperatures, so at the infrared, but more at the ultraviolet, meaning that the bulk of the dark matter will be produced at the highest temperatures of the universe. So typically at reheating or during reheating, right? Or yeah. or at the highest temperature reached by the thermal plasma. So the idea is the same, that we can have dark matter production, right, out of the standard model, but you will not have an efficient dark matter annihilation, right? So typically what we assume is that the interaction rate is comes via these non-renormalizable operators with a high temperature dependence, right? T is the temperature, right? And lambda will be a scale of new physics. So we typically have interactions which have this form. So a very strong temperature dependence, and therefore the bulk of the dark matter is produced at the highest temperature reached by the thermal plasma. So that implies that you have a scale of new physics, lambda, which is much higher than the reheating temperature. And in this case, I was telling you, the bulk of dark matter is produced at the highest temperature, meaning typically at the reheating temperature, right? So just after inflation. And here I would say that there's a strong dependence on the initial conditions, in the sense that the final dark matter abundance will have a strong dependence on the reheating temperature or on the highest temperature reached by the thermal bath. So for instance, here I'm showing you a plot of the scale of new physics, right? And T RH corresponds to the reheating temperature. So that you need for different values of N. Remember that N corresponds to the temperature dependence on this operator, the N. So in that sense, for a given scale of new physics, right, you can tune in principle the reheating temperature so that you can produce the observed dark matter abundance, right? That's the idea of the ultraviolet freezing paradigm. But of course, you can ask, okay, in practice, how can I produce this kind of operators with such a high temperature dependence? So here I'll show you a couple of examples. So for instance, you can imagine that you have the standard model that couples to dark matter via a mediator, via the S-channel exchange of a mediator. And you can imagine the scenario when this mediator is very heavy. And when I say heavy, I mean much heavier than the reheating temperature. So in that case, you can integrate out this heavy guy, and then you have a cross section. So if you want a thermally average cross section, which will scale like T squared over the mass of this heavy guy over 4. So that's, and in that case, you will naturally have FIMP UV production. So heavy mediator is one option. The other option is to have suppressed couplings, right? So if you have a dimensional coupling here, right, and here, and this coupling goes like 1 over lambda, so we're at scale. That's another way of having the same T squared over lambda 4, where lambda corresponds to the coupling, right? This scale of coupling. Or another example is having both heavy mediator and suppressed coupling, right? So in that case, you will have like T6 over lambda 4 and 4. And for instance, in these 3 cases, you will naturally have the ultraviolet freezing production. So meaning that the bulk of the dark matter is produced T reheat or at the highest scale of the highest temperature of the thermal bath. So there's a particularly well-motivated example for this ultraviolet freezing production and corresponds to the gravitational freezing. Because so correspond to this case. So for instance, imagine the mediation of gravity. So gravity can always, I mean, it's always mediating it's always a portal. The graviton is always there. So in this case, you can imagine that this scale of new physics corresponds to the coupling between the graviton and dark matter, or the graviton and standard model. And we know that, I mean, there's no freedom there. You know, graviton is just massless spin 2 that which couples with a coupling proportional to 1 over the Planck mass. So in that case, of course, the mediator will not be heavy, will be massless actually, and the coupling will be 1 over the Planck mass. So in that case, you will naturally have UV freezing when you have gravity, and that's the only gravitational that we are sure that has to be there. I mean, there's no way to avoiding it. There's no free parameter there because the only coupling is a Planck mass. It's 1 over the Planck mass. So that's one example of gravitational of ultraviolet FIMP production. So we give you a bit more of details here. So
hello, I have a question.
Yes, sure, please.
So how the nitrogen cross-section depends on the temperature in the IR FIMP case?
Yes, here is not that simple. Here you have to do exactly the same, the case as WIMP. You have to compute the cross section as a function of the center of mass energy and make the thermal average, and you will have a complicated dependence with the temperature. It's not in that sense the ultraviolet is much simpler because typically it's just a power law. For ultraviolet, that's what you typically have, T to some power, like this. However, in the infrared, it's not that simple. It's typically a complicated a function of temperature. Yes, it's not as simple as ultraviolet.
Yeah. Okay. Yeah. Thank you.
But for doing that is exactly the same computation that you do when computing the case of WIMP. It's exactly the same.
Okay.
Thanks for the question. Are there any further questions or comments? Okay, if not, you just interrupt me whenever you have a question and that's it. So yes, okay, I was thinking about gravity. So I was saying that an example of this UV FIMP corresponds to interaction mediated by standard model gravitons. So for instance, you can have this kind of diagrams, right? So two standard model particles that annihilate into two dark matter particles via the S-channel exchange of a graviton. So, graviton is a spin 2, a massless spin 2 that couples with a coupling which is 1 over the Planck mass. So 1 over the Planck mass here. So there's no freedom. You can compute this kind of diagram, and the cross section will be something like this: T squared over the Planck mass square times a constant, and this constant depends on the spin of the dark matter. That's it. So this is a number that you can compute. And this diagram will depend on the dark matter mass and spin. So the spin is in this here in this alpha, and on the reheating temperature. And that's it. There's no free coupling because the only coupling is the Planck mass, which is fixed. So you can compute this Rayleigh abundance. So via the external exchange of gravitons, and it will depend on the spin, so alpha, on the dark matter mass, and on the reheating temperature, and basta, finito. That's it. So here, for instance, I'm showing you a plot of the reheating temperature as a function of the dark matter mass, and this like triangular shape corresponds to the parameter space where you can compute you can reproduce 100% of the dark matter abundance. Inside, you're overproducing, so you're producing way too much dark matter. So you can see that this process is viable for typically very heavy dark matter, so 10 to the 10 or so GeVs, and for very high reheating temperatures. Yes, and it's kind of it's not surprising, at least, because you need because this process is very inefficient. So the only way to boost this process is having heavy dark matter and high reheating temperatures, right? So this is a first point. So you can produce the whole dark matter abundance just with gravity. So no need to have a Higgs portal or kinetic mixing or neutrino portal. Just gravity could do the job, okay, under such conditions. Okay, one thing is that here I'm assuming that the reheating happens instantaneously. So if you want that the graviton, sorry, the inflaton decays instantaneously. And we know that no particle, I mean, particles can never decay instantaneously. It can decay fast or with a large or with a small decay width, but it will take a finite time. So in that case, it will have a realistic decay is a non-instantaneous decay of the inflaton. So you will have a non-instantaneous reheating. And in that case, I mean, it have been shown more than 20 years back, that in the case or in the realistic case of a non-instantaneous reheating, meaning in a non-instantaneous decay of the inflaton, the standard model thermal bath could reach temperatures much higher than the reheating temperature. And this maximal temperature is called Tmax, surprise, surprise, and will correspond to the standard model thermal, the temperature, so the maximal temperature that can be reached by the standard model, which is typically much higher than the reheating temperature. And you can see this just in the case of a non-instantaneous decay of the inflaton. So here, for instance, I'm showing you a plot of the energy densities of the inflaton in blue, in dash blue, and radiation in black, right? So for instance, assuming that the inflaton has an equation of state omega, omega is just the equation of state of the inflaton. So take omega to be zero, just to be, so it's a well-motivated and easy choice. So you can see that, and all these parts here correspond to the epoch, so to the reheating, the non-instantaneous reheating. This is reheating. This is reheating. So reheating is non-instantaneous. So in this part, during reheating, you have both the inflaton and radiation. So the inflaton is scaling as matter because we are taking the equation of state zero. And in that case, the inflaton is slowly decaying into radiation. So it's producing the dark matter, the standard model thermal bath. And in that case, radiation is not free radiation. It will not scale as free radiation because it has a source, because the inflaton is decaying, is sourcing the standard model. And that's why during that period of reheating, the temperature is not scaling like 1 over the scale factor. I forgot to say, sorry, A is the scale factor here. So during reheating, temperature will scale like scale factor -3/8 instead of -8 to the -1. It's just because it's not free radiation. Inflaton is decaying into radiation. So, I mean, I'm giving all the details because I just want to motivate that reheating is not an instantaneous event. It takes a period of time, long, short, doesn't matter. The point is that during this period of reheating, the standard model bath could reach temperatures much higher than T reheat. And remember that T reheat, it corresponds to the temperature at which you have the onset of radiation domination, right? So I'm going back to the previous slide. So I was saying that you can produce the whole dark matter abundance after reheating via scattering of standard model particles. However, during reheating, so that was after, during reheating, you have that the universe is dominated by inflatons. And during reheating, you can have annihilation of inflatons into dark matter particles, again, via the mediation of graviton. So we can compute that, and it will depend again on the dark matter mass and the spin, the reheating temperatures. Again, there will be no free couplings because I'm assuming 100% gravitational mediated process. Here will nevertheless depend on the inflaton mass, right? Because the inflaton is one particle which is on the initial state. So here is basically the same plot I showed you before. So in red here, this corresponds to exactly the same process I showed you before. This is the exchange of standard model. So this is standard model into dark matter. So it is after inflation. And this in blue corresponds to the process during inflation. So this is inflaton into dark matter, right? So it's basically the same information that I was showing you before, the same plot, but here I'm having the production by annihilation of standard model, and this corresponds to the annihilation of inflaton, right? So again, theory heat as a function of the dark matter mass for a kind of random choice of the inflaton mass. I mean, well motivated, but still kind of arbitrary value of the inflaton mass, which is 3 times 10 to the minus 16 GeVs, as in the case of Starobinsky inflation. So you can see that typically the annihilation of inflatons is dominant. However, there are some regions of the parameter space where you can have the annihilation by of standard model particles. This corresponds to scalar dark matter, but the same I can use the same plot, but now for fermionic dark matter, this was for scalar dark matter, and for vector dark matter. Yes. So this corresponds to gravitational FIMPs in the sense that they are produced via the mediation of gravity, and therefore the connection is via this non-randomizable operator suppressed by the Planck mass. Okay, so I don't know if there are questions. If not, I will go into a kind of slightly different topic, which is now will allow for dark matter self-interaction, because till now we have implicitly assumed that dark matter has no sizable self-interaction. So dark matter is not interacting with itself, right? So we're assuming that once produced, dark matter is basically, I mean, have no interaction with itself whatsoever. So here, what the question is, what happens if we allow dark matter to self-interact? So that's basically what he told you. So far, we have focused on dark matter, an interaction between dark matter and the standard model, right? So when we say FIMP, WIMPs, FIMPs, UB and UR, we talk about the interaction between the two sectors, and we have ignored possible self-interaction. But what about possible dark matter self-interaction? Okay, and when talking about self-interactions, for instance, in the case of scalar dark matter or vector dark matter, we can have these quartic interactions. And if these quartic interactions are effective, quartic is just an example, right? We can have kinetic equilibrium. And when we're talking about kinetic equilibrium, I mean that dark matter, the dark sector, could be characterized by a dark temperature, which in principle or in general could be or is different from the standard model one. So we have two sectors that both reach equilibrium, kinetic equilibrium, sorry, but not with them between themselves, but on their own. So both sectors will be characterized by temperatures, but by different temperatures. So the photons will have one, and dark matter will have another temperature if the kinetic equilibrium is reached. So via elastic scattering. So two dark matter into two dark matter. So elastic scattering. However, if interactions are sizable enough, we can have more than elastic scattering. We can also have non-elastic scattering. And that means that we can have number changing interactions. And here you see that I'm only having quartic interactions, right? Quartic here, quartic interactions here, quartic here, here, and here. This is just an example. Huh? So if I have this number changing interaction, I can reach chemical equilibrium in the dark sector. And that means that in this example, I can have 4 to 2 and 2 to 4 interactions. So that means that not only the dark matter will reach kinetic equilibrium, it will not only have a temperature, a dark temperature, but we can also have chemical equilibrium in the sense that we have this number changing interaction. And that could be very interesting. Because here I'm showing just an example of what could be the dynamics of the dark sector. So I have here two plots. So one corresponds to the dark matter abundance, so the dark matter yield, dark matter number density normalized by the entropy density as a function of this variable x, which is dark matter mass over temperature. And here I show you in downstairs a plot of the temperatures as a function again of 1 over the mass over the standard model temperature. This is standard model, sorry. So by construction, it will drop like 1 over x by construction. So the idea is that we have first a production at a FIMP, so an out of equilibrium production, right? Exactly as happened with FIMP, right? So the dark matter abundance will grow slowly, exactly as in the case of the FIMP. However, if we have sizable self-interactions, the dark matter will reach kinetic equilibrium via 2-to-2 interactions. That means the dark matter will have a temperature, and this temperature will be of the same order of the standard model temperature, because after all, the dark sector is produced out of the standard model. So we expect the two temperatures to be more or less the same. The dark matter is relativistic, so we will also scale like 1 over the scale factor. So these two curves will be, for the temperature, will be exactly parallel. However, at some point, we'll reach chemical equilibrium. So before that, dark matter population will rapidly raise via out of equilibrium 2 to 4. So we can have production of dark matter out of itself. So 2 dark matters annihilating into 4 dark matter particles. And the price to pay is we'll have a decrease of the temperature. So after all, we're trading 2 very energetic dark matter particles into 4 particles at rest. We're trading kinetic energy into mass, right? So we are producing the dark matter number density is increasing, and the dark matter temperature is decreasing. So we are trading temperature, so kinetic energy into mass. And at some point we reach chemical equilibrium, meaning that 2 to 4 and 4 to 2 reactions happen both and happen at the same rate. So we reach a plateau, it's equilibrium. So again, the two sectors are relativistic. The two temperatures scale at the same, like 1 over the scale factor, as relativistic particles. And at some point, you will reach dark matter annihilation, the annihilation, meaning that we will have the freeze out. So this is exactly the same Boltzmann suppression that we have in the case of wind, right? So we have the opposite effect. So dark matter is annihilating. So we're going from 4 particles into 2, and the price to pay again is the contrary. So we are heating up. We're going from 4 particles into 2 very relativistic particles, right? 4 to 2. So we have a rate of the dark temperature. And at some point after dark matter freezes out, so you reach the equilibrium. And so you go out of equilibrium, you reach the observed dark matter abundance. And then the temperature, dark matter is not relativistic, out of equilibrium. So it cools down much faster, like 1 over the scale factor square, right? So this is just a sketch. I don't know if a question of this point. This is just a sketch, but of course we solved the Boltzmann equation, and next slide will be exactly the same information, but just the information that comes from solving the Boltzmann equation is the same thing, but this is more complicated to understand. So again, this is dark matter abundance in the case of freezing. This line here, freezing without self-interaction. Now, if I take into account self-interaction, that's the effect that you have. So this is without the blue, and the reddish is with self-interaction. So that's exactly what I showed you. You have self-interactions. I can reach chemical equilibrium with itself, and then I will have a freeze out, a dark freeze out, and then I will get the dark matter abundance. So the impact on self-interaction is like typically a boost of the dark matter rate abundance by several orders of magnitude. And that's what we did for FIMP, right? Okay, and you can compute this boost in a model independent way. So the details that maybe I don't want to discuss here. So like making a recap. So if dark matter possesses sizable self-interaction, there are 2 effects. So dark matter could thermalize with itself, meaning that it could reach kinetic equilibrium, but it could also reach chemical equilibrium if you can have number-changing interactions, like 2 to 3 or 2 to 4 interactions. So here the question is, what is the total energy density transfer from the visible to the dark sector? what is the dark matter temperature if we reach kinetic equilibrium, and what is the dark matter number density if you reach chemical equilibrium, right? And as I told you, as I showed you before in the previous plot, is that self-interactions could increase the dark matter density in the case of freezing by the price of decreasing its mean kinetic energy. Okay, so here I'm showing you exactly the same plot that I showed you before. So red corresponds to the scattering of standard model into dark matter mediated by gravity, and the blue corresponds to inflaton into dark matter. So that corresponds to the lines. So the lines here, the lines are exactly the same lines that I showed you before. The lines. Now I'm showing you also some surface. So this surface is the parameter space that could be reached, or that could be explored in the case where you have sizable self-interaction. So the lines correspond to the normal freezing, whereas the bands, so the red and the blue bands correspond to the case where you take into account the effect of self-interaction. So as you can see, typically lower reheating temperatures could be explored, and a bigger parameter space could be explored once you take into account dark matter self-interaction. So meaning that you can reach both kinetic and chemical equilibrium within the dark sector. So that corresponds to the case of scalar dark matter. But again, I can show you the same plot for now fermions and vectors. And this was done for a ratio of temperature T max over T reheating of order 10, actually of 10. But I mean, I'm just showing you more plots. This corresponds to the case where the ratio of temperatures is like 100, right? And I forgot to tell you that this green band corresponds to the region that is in conflict with the inflationary scale. So from Planck, we know we have an upper bound from the inflationary scale. I think it's 10 to the minus 5 Planck masses or so. So this green band is the region of the parameter space which is in conflict with the inflationary scale as measured by Planck. Are there questions or comments at this point?
So in your analysis, I think assume the quadratic potential for inflaton, right?
Well, not really. You think that because of the choice of the inflaton mass?
Because I think because the temperature, I mean let's see, because during inflation, the temperature of standard model is called like a standard cosmology, right?
Actually, this is model independent, but it's true that in the back of my mind I have quadratic inflation or something like Starobinsky, because I have it's true that I'm assuming that the inflaton scales during reheating, I was assuming that the inflaton scales like matter, so that if you want oscillating in a quadratic potential. And also for the inflaton mass, I took this 3 times minus 10 to the 16 GeVs, which is typical from quadratic inflation or from Starobinsky inflation. So that's true. But this is really model independent in the sense that you can repeat the analysis for any equation of state or take an arbitrary inflaton mass. But I think, to be fair, what I have in the back of my mind is quadratic or Starobinsky inflation, because quadratic inflation is kind of in tension or maybe it's completely excluded, whereas Starobinsky inflation is still, works perfectly well. Mm-hmm. But yes. But but the main method here is independent on that. You can do it for any inflationary scenario, and the point is that there's a strong impact on the dark matter self-interaction. So they can change. So first is that you can produce the whole dark matter abundance just using the gravitational portal. So this corresponds to gravitational dark matter in the sense that it's only connected to the visible sector via gravity. So there's no Higgs, no any portal, just gravity. And we know that you cannot avoid that. So gravity is there no matter what. And on top of that, self-interactions, possible dark matter self-interactions could have a strong impact. So modify what your expected parameter space. Yeah.
Thank you.
Thanks. But I like this question because it's true that if we till now I have been kind of skeptical about how was inflation and how was reheating. So that's why we want to have something. We want to embed this in a more realistic scenario, in a more realistic inflationary scenario, a more realistic reheating scenario. And that's why with Yongshu we study basically the same idea, but now in a particularly well motivated scenario correspond to the polynomial inflation. So before talking about polynomial inflation, I will show you the result. For sure you're aware of this. So this is a paper that appeared last week, maybe 2 weeks back. So it was October the 1st. So these are the very latest results from BICEP and Keck collaboration. So this a plot of R, which is the tensor to scalar ratio, as a function of the spectral field of the scalar spectrum. And so there's a lot of information here. So this greenish region corresponds to the the result of the Planck collaboration, right? So those were the latest results until September this year. So 3 weeks back, these were the latest results. And what this paper did is that it updated the Planck results, now taking into account BICEP and Keck results. And now when we take that into account, you're going from this greenish region to the blue region. So the allowed parameter space is much smaller, right? So we're still compatible with the same spectral index, 0.965, something like this. But the big difference is that now these recent results require much smaller tensor to scalar ratio, much smaller value of R. Before the upper bound was 0.11-ish or 12, I don't know, this. And now the new bound is more like 0.05. So it's much smaller. And in particular, this put into serious problems the monomial inflationary model. So these are the prediction for phi to the 1, so linear on phi squared, and phi power 2 over 2/3. Yes. So basically, these three cases, or basically all the monomials, because all the monomials will lie in this yellowish band, will be in tension. I mean, before they were already in tension, but now it's much stronger. So I think this corresponds to 1 and 2 sigmas, if I remember correctly. So they were all outside this preferred region by BICEP, Keck, and Planck. So if monomial inflation is under tension, the natural next step beyond monomial is polynomial inflation. So we are happy. And I have put a smiley face here. So what the idea of polynomial inflation is that we will take single field inflation, now characterized by the most general renormalizable inflaton potential, so phi is all inflaton. So I take these terms, so quadratic, cubic, and quartic. Of course, we can also take, we can also have a constant term, which corresponds to the cosmological constant. However, it will be just, it's too small, and it will make no effects here in the phenomenology of inflation, at least at the inflation at the moment of inflation. We don't care about the cosmological constant, so that's why I'm disregarding it. Okay, the input. So we can have a constant here that we are disregarding because it's just very small, and we can also have a linear term on phi. However, this linear term can be absorbed via a field redefinition. So we can only, I mean, it's enough to take these three terms. So this one is too small, and this one can be absorbed via field redefinition. So if you take, it's okay if you take the quadratic, the trilinear, and the quartic term, right, for inflation. Of course, we don't want to take like the most general, because what we want is to have a slower inflation. So we need a potential which is very flat. So one way to guarantee that is imposing an inflection point. An inflection point means that at some point of the potential, both the first and the second derivatives are exactly zero, right? So we want a potential of this shape, which is very flat, and having an inflection point. An inflection point naturally appears if you take this kind of relation between the parameters B, C, and D, and if you have this relation, you have an exact inflection point at phi 0, right? And that's something that we want, because we want the potential to be flat in order to have slower inflation. And if you have an exact inflection point, you have a potential of this shape, right? So you had initially three free parameters, B, C, and D. We take one condition, so you have two free parameters, D and phi 0. So D is basically the overall normalization of the potential, and phi 0 corresponds to the inflection point. However, the bad news is that the exact inflection point will not work. It will not work because we will not be able to fit the Planck data. However, we can have an almost exact inflection point. So, and this departure from the inflection point will need a small tilt in the potential. This will be parameterized by this guy beta. So beta equal to 0 corresponds to the exact inflection point. However, as I'm telling you, beta equal to 0 doesn't work. We need a beta very small, but finite. So that's the kind of potential that we'll use, characterized by three free parameters. D, again, is the overall normalization of the potential. Phi 0 is the position of the inflection point, and beta is the deviation, the small parameter that parameterizes the deviation from the inflection point. It's giving a small tilt at the inflection, or at the near inflection point. Okay. With such a potential, it's possible to compute the slow roll dynamics. So we can compute the first, the second, and the third slow roll parameters. That depends basically on the derivative of the potential, and the potential and its first, second, and third derivatives. So we know when slow roll is breaking down. So when exactly the first inflation slow roll parameter is equal to 1, that corresponds to the end of inflation. And with that, we can go, if you want, 60 or 50 e-folds back in time, and compute what are the predictions for the tensor to scalar ratio, for the scalar tilt of the spectrum, and the normalization of the scalar power spectrum, right? And alpha correspond to derivatives. And these parameters are not all free parameters. Remember, we know exactly what normalization, it's the Covey normalization, so the normalization of the power spectrum, and we know what's the scalar tilt. Remember that we have this from Planck, right? We know that NS has to be 0.96 or so, right? So taking that into account, we can have, I mean, there are no more free parameters. So the alpha, so the tensor to scalar ratio tends to be super small, which is good in the sense that it's it's within the measures. So the measurements say that the tensor to scalar ratio R has to be very small. In our case, it's super small, so it's okay because it's fulfilling all the observations. However, the bad thing is way too small to be detected by next generation observatories. This means that basically there will be no primordial gravitational waves. So that's kind of bad. However, the parameter alpha, which corresponds to the tilt of the tilt, if you want, to the derivative, it's within it's within the bound, the actual bound, and could be detected by next generation experiments. Okay, so all that for saying to say that this model is perfectly in agreement with recent observations of the inflationary potential of the inflationary observables like R, the tensor to scalar ratio, and the tilt of the scalar power spectrum. Okay, and also the inflaton mass will depend on the position of this of the inflection point, and in particularly we know that the inflation in the inflaton mass will be somewhere between hundreds of GeVs and 10 to the 11 GeVs, right? Okay, and that will depend on the position of the inflection point. Now, what's the dynamics of reheating? So of course, the inflaton has to be coupled to the standard model, and it's typically coupled via the Higgs, via this kind of Lagrangian. So you can have a linear coupling between the inflaton and the Higgses, or between two inflatons and Higgses, right? So basically the Higgs portal. So then we can compute the perturbative decay of the inflaton. So the inflaton will decay directly into a couple of Higgses, and you can compute it. Will depend on this coupling lambda 1, 2, which is a dimension full parameter that controls the coupling between one inflaton and two Higgses. And therefore, you can see that depending on the inflaton mass, that's here I'm showing you a plot of the reheating temperature as a function of the inflaton mass, and Tmax, because remember that the inflaton is not decaying instantaneously. So the standard model thermal bath could reach temperature much higher than the reheating temperature, right? So here you can see that both T reheat and Tmax could span over several orders of magnitude, right? And as a function of inflaton mass. And here on the right, I'm showing you a plot of the ratio Tmax over T reheat. Before I was assuming in the previous plot, so in the previous paper, if you want, I was assuming this ratio Tmax over T reheat of order 100, 10, 1000. So it was like imposed by hand. But here in this model, this ratio Tmax over T reheat is not a free parameter anymore. It comes once you fix, so for instance, the inflaton mass and the decay width. So this parameter lambda 1, 2. So Tmax over T reheat again spans over several orders of magnitude. It can be between 10-ish or so and 10 to the 7th and to the 8th. So you can have a big gap between Tmax and T reheat, meaning that the reheating era could be quite long. And now, how could the dark matter produced in the early universe? Here there are different scenarios. So we can have, okay, and here we are assuming fermionic dark matter, so a Dirac fermion. So we have the piece of the Lagrangian that controls dark matter. I mean, we have this kinetic term. We have a mass term for the Dirac fermionic dark matter, and you have a direct coupling with the inflaton. So phi, remember, the inflaton. You can have phi chi bar chi, where chi is the Dirac dark matter. So there are several ways for producing dark matter. So one is the direct decay of the inflaton. So inflaton decaying directly into a couple of dark matter particles. We can also have the 2-to-2 scattering of inflaton during reheating. So one possibility is that this 2-to-2 scattering of inflaton into dark matter is controlled via the graviton, right? The massless spin 2 that couples like 1 over the Planck mass. But you can also have the scattering mediated by the change of an inflaton, right? Or a T channel mediated by dark matter itself, right? So you can have these channels. So this corresponds to the initial state of 2 to inflaton during inflation. But after inflation, what you have is standard model particles. And in that case, you can have, that will be the usual UV freezing. So where you have the scattering, so annihilation of standard model particles, either mediated by the graviton or mediated by the inflaton if the Higgs is the particle initial state. So for the dark matter boration, in this scenario is very rich because we have a lot of alternatives. So different production channels of the dark matter. So let's go one by one. So the first one corresponds to the direct decay of the inflaton. So this process here. So this corresponds to the direct decay of the inflaton. So again, inflaton decaying to 2 dark matter particles, which in this case correspond to Dirac fermions. So you can compute this decay width, right? So the decay width will have this shape. And you can compute what the dark matter, find the final dark matter abundance, which is this one. We have a strong dependence on T reheat, because after all, you remember, you have to keep that in the back of your mind. These all are UV dominated process. So the bulk of the dark matter happens at the highest temperature reached by the thermal bath. And in particular here, it will have a strong dependence, a strong linear dependence on the reheating temperature, but also on the branching ratio and the inflaton mass, right? So here in this plot, I'm showing you what's the Yukawa coupling YX, Y chi, and remember Y chi is just the Yukawa between the inflaton and dark matter. So this plot showing you contour lines for the Yukawa coupling needed in order to reproduce 100% of the whole observed dark matter abundance. So in the plane of T reheat as a function of the dark matter mass. So one interesting is that you can produce the whole dark matter abundance basically for all dark matter masses. So from very light dark matter in the MeV or KV ballpark up to masses as high as the inflaton mass. And here again, I have okay, remember that here the inflaton mass is not a free parameter anymore. It will depend on where the inflaton, the inflection point takes place, right? So of course the dark matter has to be lighter than the inflaton mass, because you want the direct decay of the inflaton. And also dark matter cannot be super light because you will enter in troubles with the Lyman alpha, so with the structure formation. But otherwise, I mean, you can see that dark matter could be KVs, GVs, TVs, up to several hundreds of PVs, right? For of course for very small Yukawa couplings. So the point here, they can produce the whole dark matter abundance only via the decay, the direct decay of the inflaton. But I was telling you that that's not the only channel possible in this model. So you can have UV production, FIMP UV production during inflation via the inflaton scattering. So again, inflatons can scatter into dark matter particles via the decay, the F channel exchange of the graviton, the F channel exchange of an inflaton, or the T channel exchange of a dark matter particle, right? So you can compute this kind of processes. However, this typically is not the dominant. I mean, you can compute what the dark matter yield, However, as I was telling you, this typically not the dominant, so it can only compute to few percent of the total dark matter abundance. So this process is there, we have included, however, it's typically subdominant, giving rise to a small fraction of the total dark matter abundance. And last but not least, we have the usual UV freezing dark matter production via the scattering of standard model particles. This corresponds to the scattering after reheating. So you have that particles of the standard model bath can produce dark matter particles, again, via the S-channel exchange of either a graviton or an inflaton. So real inflatons are not there anymore. However, you can always have the virtual exchange of inflatons. And again, you can compute what's the total dark matter abundance produced via these kind of processes. And again, this tends to be subdominant. This channel is subdominant because the inflaton is very massive. So this will be very, very suppressed, not only because of the couplings, but also because of the mass of the inflaton, of very heavy inflaton. And this typically, again, suppressed because the coupling, so the coupling is plant mass suppressed. So again, this contributes maximum to few percent of the total dark matter abundance. So all that for saying that even if we have several processes, typically this one, so the direct decay of the inflaton is the one that is going to dominate the total dark matter abundance. So I do not have questions at this moment, otherwise I'm kind of done.
Sorry, I have a question.
Sure.
What you introduced, the interaction which you introduced breaks the flat, slower condition. Sorry. I meant is what the interaction which you introduced breaks the shift symmetry of phi, right?
No, I don't have a shift symmetry.
The slower impact to the
Yes.
slower condition, right?
Uh-huh.
And I think you need a very flat potential to reproduce the very small r.
Mm-hmm.
And I think the interaction which you introduced impact to such a conditions.
Yes, it's true. Let me see if I understood your question. So it's true that I start with a very general potential.
Yes.
So this, and in general, this potential will not fulfill the slow roll because it could be very steep. However, I'm assuming that I have an inflection point, and an inflection point means that it's really flat. So this is an example of the potential that we have. This is like a real example. So you can see that near the inflection point, the potential is very. If it's an exact inflection point, the potential will be completely flat. Really horizontal. However, we don't have a.
Interactions which you introduced impacts that dynamics of inflaton.
You mean interaction with dark matter, for instance?
Yeah. Or
okay. Yes. Sorry. Yes. That's now that yes. I forgot the slide on that, but it's very true what you're saying. And the interactions could spoil everything, and that's why I have here. Sorry, I forgot the slide about that. Yes, it's my fault. But we took that into account. So because when we're taking into account interaction of the inflaton with other particles, we can spoil the stability of the potential, and we can spoil the slow roll condition, so the flatness of the point of the potential. So that's why we have this condition here, what we call stability, and that's exactly I think what you have in mind. But it's true. We took that into account. So we took loop corrections of the potential due to the interaction with a standard model and with dark matter. We took that into account. But yes, yes, I forgot that slide.
Okay, thank you.
But it's very true. Yes, thanks for the question because I completely forgot that. Yes, but we took that into account, and in the paper you can see all the details. Yeah, thanks.
Okay, thank
thanks
you
for that because I forgot. Yeah, very good point. And I think yes, I'm kind of done now. So just recap. So that's freezing in general, and in particular, UV freezing, meaning when the dark matter is produced at the highest temperature of the universe. It's a completely viable dark matter production mechanism. And not only that it's viable, but it could be, first, it's unavoidable because you have gravity is always there. So there's no parameters to tune. So UV production, gravitational UV production is there. So, and it can produce the whole dark matter abundance. And it strongly depends on the dynamics at the highest temperatures of the universe, meaning if you want to compute that, you have to care about inflation and in particular about what's the heating dynamics. And in that case, the instantaneous reheating may not be a good approximation. And it's true that kind of the standard law, maybe of cosmologists, but at least of particle physics, is that the reheating is instantaneous. So the inflaton decays, end of inflation, and the inflaton decays instantaneously, and basta. But I mean, I think you can see that this could be much more complicated. Typically, universe is much complicated than what we think. So, and also one important thing is that self-interactions could have a strong impact in the dark matter genesis. And typically, what dark matter self-interactions do is that they boost rate abundance, and that's good. And the price to pay is that you're decreasing the dark matter kinetic energy, right? So you're trading kinetic energy into mass. So you're boosting the dark matter number density. So again, to emphasize that gravitational dark matter production is unavoidable, just because it's gravitational, there are no couples to tune. And you can, in that sense, you can have dark matter production out of standard model particles via the graviton mediation, or during heating via inflaton, inflaton scattering. Also, in the light of recent observations, meaning Keck and Bicep, we know that monomial inflation is in strong tension, in particular because of this tensor to scale ratio. So polynomial inflation is a completely viable alternative. Polynomial inflation near an inflection point, because you want slow roll, so you want the potential to be flat enough to have slow roll conditions. And in that case, dark matter could be produced via the direct decay of the inflaton. And thank you very much. So I think here it is written, thank you very much, but I cannot confirm. So thank you guys. So if you have questions or comments, I'm happy to try to answer it.
So, thank you very much for a nice talk. So any question or comment?
Hello, Nicolás. Thank you very much for nice talk.
Hey,
Hi.
Nice to see you.
Yes. And do you also have some plots for the vector dark matter production in the earlier slide? And so for the inflaton decay to the pair of vector dark matter, for example, are there any qualitatively basically the same as the fermion dark matter case?
The fermionic is slightly different, because you have this suppression. The suppression, I forgot what was the reason. I forgot. So you have a, well, you have a fact. It depends on the dark matter mass. Sorry, I forgot. But
okay, so my question is that, sorry, so simplify,
wait.
if I simplify the question, so do you assume that this vector dark matter mass comes from the Stickelberg mechanism in your?
Okay, yes, in that sense, it could be due to Zuckerberg, yes.
Okay,
We're putting like this mass by hand, but of course this could mean that it comes from Zuckerberg.
Okay, yes. I see.
Okay, so the point I want to emphasize is that basically the scalar and the vector are basically the same thing.
Yes.
You can see that the plots are basically the same.
Right.
However, the fermion is different because you have maybe it's raised to spin flip maybe. So you have a factor of dark matter mass over the inflaton mass that is there, and therefore is much more suppressed.
Okay.
So, but that only happens for fermion, but vectors and scalar is basically the same.
I see.
Yeah.
Thank you.
Welcome.
So you are in the Colombia now, or in Europe? Or?
In Colombia, yeah.
Okay, yeah. So midnight, almost midnight.
No, it's it's
no?
9:20 here.
Okay, yeah. I see.
So it's still Monday here.
So can I ask a naive question?
Sure, please.
I couldn't understand the prospects of detections of your FIMPs in these scenarios because I mean you mentioned that from the inflation they are constrained, but what about dark matter detection experiments?
Yes, so that's typically a problem of FIMP because I think when this FIMP idea was introduced, I mean, we love WIMPs, right? We love WIMPs because we can produce in collider, have direct detection, indirect detection, everything. However, we haven't detected. So FIMP is like an exit in the sense that you know how to escape to all these super big constraints. However, now the problem is that by construction, FIMPs are very difficult to detect. So how to detect? Well, it's a problem. In the case of infrared FIMPs, you can, it's complicated, but it's possible. For instance, if you have a light mediator, you can enhance the direct detection possibilities, or if dark matter is very light, because in that sense, you're boosting the dark matter number density, right? And therefore you can, if you go to MEV dark matter, you can use these new techniques of scattering with electrons. So there are this number of detectors that are aiming at detecting MEV dark matters, particularly when it interacts with electrons for direct detection. And also you can produce, I mean, there are some papers that claim that it's possible to produce, to detect at colliders the mediators, but I mean, it's kind of cheating, I agree. However, in the case of gravitational FIMP, that's, so 2 comments, that's very difficult, but the other side of the coin is that this is an unavoidable process. So it's true that it's not that we prefer, but it's there. I mean, the only interaction that is guaranteed is gravity, right? So this has to be there. It's like a nightmare scenario if you want. So, or at least if you want, it's very challenging, at least for the particle physics, because there's impossible to detect, well, impossible. Very challenging, let me put it this way, indirect detection, indirect or colliders. However, cosmology can give you hints. For instance, you can use scalar dark matter. I mean, there's always Lyman alpha bonds coming from isocurvature. But I completely agree that this kind of nightmare scenario. And yes, it's more cosmology that will give you hints. For instance, if you have self-interacting dark matter, you can try to address the tension in the with small scale structures. So this too big to fail, missing satellites. So, but it's true that detection is very challenging, and maybe you have to go to Cosmos more than to usual particle physics detectors.
Okay, thank you.
No, thanks for the question.
Any other question?
Hello, I have one simple question about this inflection point inflation, I mean polynomial inflation. So in the next page, you introduce parameter beta in the potential, right?
Yes, here.
So yeah, here. So I think the what happens if you assume beta is just 0?
Yes,
is it essential to have a non-zero beta here? Or not?
Yes, and that's kind of sad. I agree. but we need it in order to match the spectral index.
Mm-hmm.
But this beta is very small. However, maybe don't.
Yes, here.
I don't have the numbers how small it has to be, but it cannot be 0. This, yeah.
I see.
Like it's hard. It will be much more elegant having a exact inflection point, but yeah.
So in the original form of the potential, we have 3 parameters B, C, and D,
Yeah.
and you trade them with D and phi 0.
Yes.
And then you make a small perturbation in terms of beta. Is that right? Yeah. Okay.
Yes.
I see.
Yes.
I see.
So we have 3 parameters B, C, and D. We impose an inflection point, meaning that it's not 3 parameters anymore.
Yes.
So we have
right.
D.
Right.
So the overall normalization and the position of the exact inflection point.
Right.
But this doesn't work, so we introduce a small deviation from the inflection point. So we have like this third parameter beta.
Okay. Thank you.
No, thanks to you.
It seems no more question. Okay, then let's thank speaker again. Thank you very much.